welcome back, Stella. I hope you are doing well. So last time we saw these two types of integrals. So we saw type 1. So under integration of fraction or rational functions, we saw how to integrate this type 1 and we saw how to integrate this type 2. So today, as I said, we are going to see examples related to this type 1 and type 2. So let me show you the examples and what I'm going to do. These are the exercises. So exercises on type 1 and type 2. So these are the exercises. You are going to do all these exercises. So you can put a pause on your video and try to try these exercises yourself. So these are the ones I'm going to do. I'll do the question 1, I'll do the question 7, I'll do the question 8, and I'll do the question what is it? I'll do the question 11, I'll do the question 12, and I'll end up by doing the question 13. Yeah, those are the questions I'm going to do. For the rest, you are going to try it yourself. If you're already capable of doing all of this, you will have a perfect mastery of the type 1 and type 2 under integration of fractions. Before going into these exercises, I want to remind you some formulas in trigonometry that will be very important for you. So let me go back to let me create a sheet. Okay, now I want you to remember these formulas because I'm going to give you the generalized forms of these formulas. I think you can remember this formula, this well-known trigonometric formula, that cos squared theta plus sine squared theta equals to 1. Everyone who did at least basic elementary mathematics must know this. So there's this other formula which results from this one, which is 1 plus tan squared theta being equals to 1. Okay, there are these two if I'll say yes, these two other formulas which are called double angle identities. The first one is sine 2 theta is always equals to 2 sine theta cos theta, and this last one, cos 2 theta, is equals to, it has three forms. The first one is cos squared theta minus sine squared theta. It can also be equals to 2 cos squared theta minus 1, and it is also equals to 1 minus 2 sine squared theta. Okay, from these formulas, let me give you the general forms. For every n belonging to the set of real numbers, look at this. For every n, let's say, yes, for n belonging to the set of real number, the first formula, cos square of n theta plus sine square of n theta is always equals to 1. The next formula will be 1 plus tan square of n theta will always be equal. Oh, this is sec square theta. That was an error. Will always be equals to sec square of n theta. Okay. The next one, sine of n theta will always be equals to, there will be these two. Now, what do you notice here? When I write sine 2 theta, what happened to the angle here? It's like I simply did what they simply did. What they took this 2 theta and divided by what? By 2 to have this theta. So if I'm having n theta here I must necessarily have sine of n theta divided by 2 times cos of n theta divided by 2. You understand? For the last one, cos n theta must be equals to three forms. We will have cos square n theta minus sine square n theta. and the next one will be if you notice here, the angle was what, 2, and they divided here this 2 theta by what, by 2. So here we're going to have 2 cos square n theta divided by 2 minus 1, and here naturally we're going to have 1 minus 2 sine square n theta divided by 2. So let me take a small example to illustrate this. Let's say you are to calculate sine 3 theta. This sine 3 theta, I can write it like this. This sine 3 theta will simply be equals to 2 sine what? 3 theta divided by 2 cos 3 theta divided by 2. If you want, take a calculator. Let's do a small test. If you take your calculator, you replace any angle here, you see that you have this result. You always have this result. So these are the general form. From this basic form, these are the general forms of, if I will say, these formulas. So it's very important for you to master these general forms because they will be very helpful to you. Like for example, when you will be reading a topic trigonometry, when doing trigonometric proofs, yes, they will be very important to you. When they will even help you in integration, you understand. So without wasting time, let's go to the exercises we had to do. So I'll start by this first one, the integral of cos x minus sine x all over sine x plus cos x. Okay, let's go to the thing. Okay, let me go to the next sheet of paper. Wait, for example, a minute. Okay, exercises on type 1 and type 2. Okay, the first one was the integral of cos x minus sine x all over cos x plus sine x dx. Okay, let's try to observe this integral. When we look at this integral, what do we notice? When I differentiate this cos, what do I have? I have this minus sign. When I differentiate this sign, what do I have? I have this cos. This means that this bottom, the derivative of this bottom is found what? At the top. That means we are already in the form f prime of x dx all over what? F of x. That's already the form in which we are. So what I will do is that this integral would simply be equals to what? This integral. Okay, let me do this. Let me try. Since d of cos x plus sine x is equals to, always try to put this step, it can be helpful. Yes, that shows that you understand what you are doing. Is equals to cos x minus sine x dx. It implies the integral of cos x minus sine x all over cos x plus sine x dx. So what does this our rule this type 1 says? So I will replace this top by what? I'll replace the top by d of f of x. So I'll replace by d of the bottom. So this will be equals to the integral of what? D of this cos x plus sine x all over what? Cos x plus sine x. Now we are already in the form where it's like we're integrating dx on x, which is simply lim of the absolute value of x. So this will become simply lim of the absolute value of cos x plus sine x plus our constant of integration where k belongs to r. That's simply how, that's a simple integral. You understand? You see how it's very simple. When you master your rules, you basically do things in a very simple way. So let's go to the next one. Question, I said question, what is it? Question 4. Okay, let's do question 4. Question 7, pardon. Question 7, which says integral of e to the 3x all over the square root of 3 plus e to the 3x. Okay. Question 7. We have question 7, integral of e to the 3x dx all over the square root of 3 plus e to the 3x. I hope that's it. Exactly. Okay. Let's try to observe this. I'll first write this back as integral of e to the 3x dx all over 3 plus e to the 3x all that raised to the half. Okay, what do we notice? If I differentiate this bottom, if I try to differentiate this d of 3 plus e to the 3x, if I try to differentiate this, when I differentiate this first one, it gives 0. Since I'm differentiating with respect to x, this would give 0 times d of x plus, I differentiate this other one. How do you differentiate e to the u? To differentiate e to the u is simply u prime e to the u. That's it. So I will have this 3 times e to the 3x times what? Dx, since I was differentiating with respect to x. So basically when I differentiate this, I will have what? 3e to the 3x dx. But what do we notice here? We notice that there is a 3 that's missing up here for us to have to recognize this top as what? The derivative of what is inside here. So let's first rearrange this. To rearrange this, we're going to multiply top and bottom by what? 3. So this will be equals to 3 on 3 integral of what? E to the 3x dx all over what? 3 plus e to the 3x raised to the half. So let me go on the next sheet. Wait, let me go on the next sheet of paper. So this will be equals to, I'll bring back the 3 inside. This will be equals to 1/3 integral of 3e to the 3x dx all over what? 3 plus e to the 3x raised to the half. Okay, everything is already okay. What do we notice? When we differentiate this, we basically have this top. So we are already in which form? We're already in the form f prime of x dx all over what? F of x to the n. So what is the next step? The next step is simply to write back this as d of what is inside here. So this will be 1/3 integral of what? D of 3 plus e to the 3x all over what? 3 plus e to the 3x raised to the half. Now this I will write it back as 1/3 integral of what? 3 plus e to the 3x raised to the minus a half d of 3 plus e to the 3x. Is that okay? Now this is already in the form integral of x to the n dx. And how do we integrate this? We simply write x to the n plus 1 all over n plus 1 plus a constant of integration, because this big X is the same as what is inside here. So this is the same as what is inside here. So this will be simply equals to 1/3 times 3 plus e to the 3x raised to the what? Minus a half plus 1 all over minus a half plus 1 plus our constant of integration. Is that okay? So this 1 minus a half, this is a half. Since it is 1 on this, the 2 will go up. So this will be equals to 2 on 3, 3 plus e to the 3x raised to the half plus our constant of integration. So it implies the integral of e to the 3x dx all over the square root of 3 plus e to the 3x will simply be equals to 2 on 3 square root of 3 plus e to the 3x plus our constant of integration. Very simple. So you see how this integral is very simple. When you master the formulas, when you master your techniques, it's very simple to go about integrating all of this. So let's go to the next exercise. We've done this. Let's do this one. Let's do this one. Question 8. Integral of sec square theta plus sec theta tan theta all over tan theta plus sec theta. So that's question how many? That's question 8. So we have the integral of sec square theta plus sec theta tan theta all over tan theta plus sec theta is theta. Okay, let's proceed. The first thing is to try to analyze what is given to us and try to see if how we are going to proceed. Okay, what do we notice in this integral? We notice that when I differentiate tan, the derivative of tan is what? Sec square theta. Or sec square theta is still the same as 1 plus tan square theta. Remember that. When I differentiate tan, I have sec square. When I differentiate sec, the derivative of sec, as we've been, if you have been looking at the video, at the previous videos, you quickly remind yourself that the derivative of sec is sec theta tan theta. So we basically notice that the derivative of what is below is basically equals to what is at. So the bottom part, the derivative of the denominator is basically found where? At the numerator. So we are already in the form. This already we are already in the form f prime of what? F of x dx all over what? F of x. We're already in this form. You understand? So since g of tan theta plus sec theta is equals to what? Sec square theta plus sec theta tan theta g theta, it implies the integral of sec square theta plus sec theta tan theta all over tan theta plus sec theta g theta will be equals to what? What does this our whenever we are in this case, what are we supposed to do? I'll just replace this top times this g theta by what? By g of the bottom, because this is what it says here. So this will be equals to the integral of g of tan theta plus sec theta all over what? All over tan theta plus sec theta. So here we are already in which case? It's like we are integrating g of x all over what? All over big X. So the answer here is what? Ln of the absolute value of x. So what is here is the same as what is inside the g. So this will simply so this implies the integral of sec square theta plus sec theta tan theta all over tan theta plus sec theta g theta will simply be equals to ln of the absolute value of tan theta plus sec theta plus our constant of integration. Very simple. You see how they are very simple, these integrals. When you master your procedure, everything becomes very simple. So let's go to the next exercise. What is it? We are to integrate question 11, cot x dx. Okay, question 11. We are to integrate the integral of cot x dx. Okay. How do I integrate this? The first thing is that I will write completely what is cot. We know that the cot x is simply equals to 1 on tan x dx, which will be equals to what? This will be equals to the integral of what? 1 all over sine x all over cos x dx. So this will be equals to the integral of cos x all over sine x dx. Okay, if you remember clearly, I gave you already at the beginning of the lectures, I gave you already uh, this result, the result of this integral, and I asked you to remember it, to master it. I think there were something like 10 formulas, 10 remarkable integrals that you were supposed to remember. So at this stage, you are supposed to even give me this answer without me proceeding to this. So this is just a proof of how this integral that I gave you at the beginning comes out. So this will be equals to, okay, at this stage, what do we notice? What do we notice at this stage? A minute. What do we notice at this stage? We notice that we differentiate this bottom, when I differentiate this bottom, what do I have? I have what is at the top. So this is already in the form f prime of f of x dx all over what? F of x. So since g of sine x is equals to what? G is, pardon, is equals to, since g of sine x is equals to cos x dx. When we differentiate this, we differentiate, it gives cos. Since you were differentiating with respect to x, you multiply by what? Dx. This is something I've been explaining since the previous videos. So since when you differentiate sine x, you have cos x dx, it implies the integral of cos x on sine x dx will be equals to what? We just apply our procedure. So I'll replace this cos x dx by what? D sine x. D of sine x all over what? Sine x. Now we're already integrating something of the form d of x all over what? X, which is, we clearly know that the answer is what? Ln of x. So this implies the integral of cot x dx will be equals to ln of the absolute value of sine x plus our constant of integration. And you clearly see, this is just to show you, if you are to integrate, if you are to differentiate ln of sine x, how do you differentiate ln of u? The derivative of ln of u is simply u prime on u. If I differentiate this, I differentiate what is inside. This will give me cos x on what? Sine x, which is the same thing as cot x. You understand? So that was all for this question. Let's go to the last one. I think, yes, this last one, question 13, which is integral of cos to the 4x all over y plus 4 sine 2x cos 2x. Okay, let's go to a next slide. This is question 13. Question 13, we have the integral of cos to the 4x all over 1 plus 4 sine 2x cos 2x all over 1 plus 4 sine 2x cos 2x dx. Okay, the first thing I'll do in this integral is to, first of all, if you look at this integral, this bottom clearly, especially this part, what do you notice about this part? What do you notice? What I can notice about this part is that 4 sine 2x cos 2x, I can write it back as 2 times 2 sine 2x cos 2x. Now, what is this? This is simply equals to sine what? Sine 4x, because our formula says what? Sine of n theta is equals to what? 2 sine n theta divided by 2 cos n theta divided by 2. Since we are having here, so on this side, these two times this is the half angle. So to half what is on this side, I just multiply this what by 2. I don't know if you are trying to get what I'm saying. So if here, so I don't know if you're trying to get what I'm saying. Since I was having 2 and 2 here, it means on this other side I must have what? 4. I must multiply this angle by 2 because this is a half. So to have this one, I must multiply this half by 2. Okay, so this integral, by recognizing that this integral, it is the same thing as cos 4x dx all over what? 1 plus 2 sine what? Sine 4x as what we recognize here. So the whole of this, because this will be sine 4x plus times this 2, it will give 2 sine 4x. Okay, let's continue. Let me wipe this. Okay, that's already very interesting. Now, what do you notice about this bottom and this top? What I can notice is that, let's try to differentiate this top. If I differentiate this bottom, 1 plus 2 sine 4x. When I differentiate this one, wait a minute. When I differentiate this one, that will give me 0. So that will be 0 times dx plus, when I differentiate this, I have 2 into, how do I differentiate sine u? How do I differentiate sine u? I simply differentiate. To differentiate sine u, you simply use the chain rule, which will be equals to u prime times what? You differentiate this times the derivative of what? Sine u. So you differentiate. This will simply give you, if I'm to apply this times the derivative of this without taking into consideration that this is simply u. Let me explain what it means. So if I'm to differentiate sine 4x, I differentiate what is inside. This is my u. I differentiate it. It gives me 4 times. I then differentiate sine u. When I differentiate sine u, I have what? I have cos u. So this gives me cos u. What was u? My u was simply what? 4x. That's it. So this will be equal to 4 cos 4x. I think you understand what it means. If you want, you simply use the chain rule, dy du dx times equals to dy du times du dx. This is the function you are supposed to differentiate, sine 4x. So your u is what? 4x. It implies this is your y. It implies your y must be equals to what? Sine u. Dy du, when I differentiate y with respect to u, I have what? Cos u times, this is my u. I differentiate u with respect to x, I have what? 4. So this gives me 4 cos u, and my u was 4x. It gives me 4 cos 4x. So that's the same approach. So let me wipe this. Let me try to wipe this. So we were at this level. So when I differentiate this, I have 0 times dx plus, when I differentiate this one, I will have 4 cos 4x times dx, since I'm doing an implicit differentiation. So my d of what? 1 plus 2 sine 4x, I basically see that it simply equals to what? It simply equals to 8 cos 4x dx. So when I differentiate this bottom, I'm supposed to have at the top 8 cos 4x dx. So for me to have exactly this at the top, what am I supposed to do? I'm supposed to multiply top and bottom of this integral by what? By 8. So let me wipe this. Let me wipe this. So this will be equals to 8. So this will be equals to 8 on 8 integral of what? Cos 4x dx all over what? 1 plus 2 sine 4x times sine 4x. Okay, now we're going to bring this 8 inside. This will be equals to 1 on 8 integral of what? 8 cos 4x dx all over 1 plus 2 sine 4x. Okay, everything is already very interesting. So when we look at this, we see that we're already in which form? We're already in the form f prime of f of x dx all over what? F of x. Okay, since the derivative of what is at the bottom, 1 plus 2 sine 4x is equals to 8 cos 4x dx. This implies this implies um, this implies the integral of cos 4x dx all over 1 plus sine plus how is it even? Plus 4, wait, let me write this, plus 4 sine 2x cos 2x will be equals to what? We are here will be equals to 1/8 integral of what? I replace it by d of the bottom, so d will be equals to d of 1 plus 2 sine 4x all over what? 1 plus 2 sine 4x. So this is already, it's already like we are integrating d of x all over big X, which is simply ln of the absolute value of x. So this will be equals to 1/8 ln of the absolute value of 1 plus 2 sine 4x plus our constant of integration. So if I'm to write back this as this, it becomes 1/8 ln of the absolute value of 1 plus this sine 4x is the same thing as 2 sine 2x cos 2x. So this will become 4 sine 2x cos 2x plus our constant of integration. That was all. Very simple. So I hope through these small examples we did, you try to grab the basic techniques that are involved in solving the integrals of rational functions of type 1 and type 2. So you will be left with this. Try to do the rest of the exercises. If you face any difficulty in solving any of them, you just tell me in the group and I'll guide you through. So if you are capable of solving, I think all these exercises, you no more face problems in integrating rational functions of type 1 and type 2. So see you in the next video for us to continue with integration of rational functions. Okay, see you in the next video.